Welcome everybody. So our speaker today is Professor Andrzej Maciejewski from the University of Zielona Góra, who will tell us about the Newtonian and relation to Galois or even about non-integrability.
So, welcome everybody. So first of all, I would like to thank the organizer for invitation. It's for me a great honor and a challenge to talk in this place. And subject, and I will talk about classical n-body problem. By classical, I mean Newtonian n-body problem. But before I start with science, I would like to make a few remarks concerning problems. When we start our career as a scientist, we are very ambitious and we have great plans to solve century problems. But after a while, we notice that, okay, probably we will not obtain a Nobel Prize, and most of us do not write because of this a letter to Nobel Committee saying that, okay, in our preferences, science is not on the first place, and we adopt our ambition and plans to the request of real life, so publish or perish. So we find the problems which we are able to solve, and among them there is levels. There are problems that we just solving them, we say, okay, I am able to solve this problem at once. There are such that, okay, I can try and I do my best. And there are problems which are say, okay, this is something hard. If I will have time, I will try. And finally, there are problems about which we can say, okay, this is above my possibility. Yeah, I am too weak to solve. And I will report you solution of the problem of integrability of n-body, and it was my dream that, okay, if I know that it is above my possibility at once, but it happened that after long road, at least I have found a solution. I am very proud of this, and I want to share my pleasure with you about this, and I hope that I will show you how this challenging problem, when you find the proper way, is not so hard, not so difficult. Yes, so that it is like that, like a miracle that you was able just to do this, to solve this. Yeah, okay, and so let us start with science. Okay, this result is a result of my cooperation with two co-authors of this work. This result was sent to publication to Journal of European Mathematical Society, and it is already accepted for publication. Yeah? So co-authors of this paper are Maria Przybylska, also from University of Zielona Góra Institute of Physics. He is not Chinese, by the way. And Thierry Combeau from France, Burgundy University, a very brilliant guy. And so, thanks to this clever collaboration, we together succeed. So this is not only my success, but also all of us here in this group. So we started now from the problem. I will talk about integrability. And of course, you as a physicist, you know what does it mean, the first integral of differential equation. Yeah? And what kind of problem is when we ask, okay, I have a system of differential equation, and can you tell me if the system of differential equation possess a first integral or not? Can you answer this? Just, okay, you immediately ask, well, the first integral can be, you know, polynomial, rational, whatever, analytic, yeah, continuous, it is enough. So we specify the class of function, but we have to look. Okay, so the easy question, you have three equations, in R3, yeah, quadratic right-hand side, and as an exercise, try to prove that this system of three equations do not admit any polynomial first integral. And you will see where are difficulties, yeah? So to answer this question is a really challenge. And in fact, there are of course several methods to try to answer this question, but in fact, there are only few. And we are talking about Newton equation, the simplest possible formulation of n-body problem. And this is just as a matter of fact, the point mass problem. Masses are positive. And here I will talk only about the planar problem, although the main result is can be generalized to the three-dimensional case or n-dimensional case, but with some care. Yeah? So I write this equation in such a way, and here you recognize everything what is necessary. And what we know about this, okay, we can write this equation as a Hamiltonian system. So Hamiltonian function has a natural form, and we know three first integrals. Yes, so more. We have energy, Hamiltonian function. We have two components of linear momentum, and C is an angular momentum written in that form. Yeah, this this integral do not commute. And the problem in the very, very classical formulation is like that. We have Hamiltonian system with n degrees of freedom. So to prove integrability, yeah, we invoke Liouville theorem about complete integrability. Yeah, so and we say, okay, we need n independent, functionally independent first integral, which are commute, and this guarantee integrability. So this allows then, at least theoretically, to solve equations by quadratures. This old word means that more or less we can write explicitly solution of our equation. So this is the classical theory about integrability. Yeah, and okay, so and it was for a long time when we talk about n-body problem, it was question if the n-body problem is integrable or not. And now, okay, just looking from this point of view, you can ask, but who cares about this? Yeah, just knowing what we know about the reality, the most probable answer to this question is, of course, that this system, when we have more than two bodies, non-integrable. Two-body problem is integrable. So that's all. And in fact, you know, this is this answer. What I have said is that one referee from mathematical journal said, "Oh, okay, so you prove theorem that this result what is simple. Everybody expects that this is like that." Yeah. Okay. So from my perspective, this is important problem because it is because of its beauty. That's all. Yeah. Nothing more to explain. Well, and let us say not few words, but few sentences about the history of the problem. You know, the history started. I start talking about the history about the Heinrich Bruns, the German scientist. He was a calculator, you know, in a very famous Pulkovo observatory near St. Petersburg. Yeah? And he published a paper about integrability of n-body problems, saying more or less that, okay, when we have classical three-body problem, then except classical case, there is no case when the system admits algebraic with respect to variables additional first integral. So shortly, without the details. And this paper make a quite big. It was important because many important people wrote about this paper. The famous among them was Poincaré, who have found a gap in the proof of Bruns, and he corrected this. Yes, so we see. And he wrote about this work of Bruns as this is very elegant. Yeah, so and later after Poincaré, it was another French guy, Paul Painlevé. He is famous because he was twice Prime Minister of France, yeah, and he in physics is very popular because of his work and because of Painlevé test used intensively by physicists. Yeah? And later was English guy, Russell Fawcett. He was very special person, but about his proof, I will tell you the reference where it is written. It was said it is not clear at all. And later, very well known Edmund Tyler Whitaker also wrote his own version. Macmillan, okay, let us skip, and Hagihara, Japanese, who wrote 8-volume textbook on celestial mechanics. Each volume has more than 1,000 of pages. Yes, so marvelous book, but I can say nothing about his proof. Yeah, and very well-known mathematician, German mathematician Ziegel, but he wrote about non-integrability of restricted three-body problem. In fact, I don't read this paper. Probably it's worth to return to this topic. But okay, and the last stage of this correction happened in 2000. This is paper of Gilliard Tossen, published in Celestial Mechanics, and just skipping all the contents, the conclusion is okay. So that the result presented is that the whole proof is much more rigorous than the previous version. Bruns, Painlevé, Fawcett, Whitaker, Hagihara. So this is curious expression, more rigorous proof. Yeah? Proof is proof, nothing more. Yes? In fact, from my knowledge, I talked with several people that it is not the end the story of this way of proving of non-integrability of n-body problem. So what next? The new history started, again in the 2000, thanks to work of Alexei Tsigvintsev, this Russian who is now in France. He published his own proof of three-body problem, and he used something which is close with respect to technique, what I will talk about. He applied the so-called Ziegler theory. I will tell a few words about this later. Yeah, and the last paper from this slide. Sergi Simon and Morales Ruiz, where he applied theory, I will also apply in my proof of the meromorphic non-integrability of some body problems. Yes, and it was first time when this theory was used. Yeah, so it is application of differential Galois theory for proving non-integrability. If you don't know what does it mean differential Galois theory, you have to ask yourself what is Galois theory. Yeah, and okay, and I will try to introduce you to this topic, in a few words soon. I hope so. Let's go, and okay, the next papers are, as you see here. I make citation of works of my collaborator who made great progress with that respect, and in fact, the part of the result I presented here is contained in this first work. Yeah. So okay. So skip the history. Yeah. And now pass to the science. Okay. When we have system of differential equation, we can talk about different kinds of integrability. So integrability means, okay, find several first integrals for given system of differential equation. Okay. So then you can call integrability, possessing a certain number of differential equations. But when you want to formulate integrability as a kind of property which guarantees solvability of your system, then you have to require more. You have to require the big enough number of first integrals or other tensor invariants of your system to be preserved. Yeah, that's all. Yeah, and okay, in the case of Hamiltonian system, we have Liouville integrability. In non-Hamiltonian system, we have Liouville theorem about integrability and Bogoyavlensky theorem about integrability, and so on and so on. So I skip all this. We'll talk about integrability I need. So as you know, when we have Hamiltonian system, we already have one integral, the conservation of energy. Hamiltonian is the first integral. Yeah. So in fact, we can when we restrict system to the fixed value of energy, we have just separated the dynamical system on this one particular energy level. So we can ask about integrability of this restricted system to this level. So why not to talk about integrability when we fix already known first integral? This is like we have in n-body problem. Yeah, I already recall what kind of first integral we have. And here is okay, but maybe give an example why this can be important. So thinking about this, there are a lot of, maybe not a lot, but there are such examples, but the most prominent one is the heavy top problem. This is another very famous system. We have a rigid body with one fixed point in a constant gravity field. Yeah? For a long time, it was a challenge problem to prove that, okay, except non-integrable cases, there is nothing to do with that respect in n-body problem. And this is very beautiful system of 6 differential equations. Yeah. So the parameters are tensor of inertia and the location of the center of mass in the body, about integrability. So we have 3 first integrals, one integral is missing for full integrability, yeah, and okay, through the long history, so the first one case was found, of course, by Euler, the second by Lagrange when the body is symmetric, and the last one, very beautiful case of Kovalevskaya when the body is symmetric, but the center of mass lies in the equatorial plane. Yeah, wonderful result, very, very non-trivial integrable case. And the last case formed, this Goryachev-Chapugin case, this is just exactly the case of partial, so integrability of the constant energy level. This constant energy level, this angular momentum is fixed to this H1 equals 0. Yeah? And it has its own value. Yes, this is just a system which is integrable. You can write explicitly solution of this equation, and this is why it is so rare. So why it is important? Because it is really very rare. So this kind of integrability is important, and I will talk about this kind of integrability now. About the method, and look carefully what is on this slide. I consider differential equation, but you know, fact that the dependent variables are complex, it's not so important. The important thing is that I assume that time is complex, and we know that the time is complex. Yeah, this change a lot. Yeah. Really a lot, because you can travel on the time on different paths. Yes, so from complex analysis, you know that the function of complex variable, as a matter of fact, is a function of two variables, real and imaginary part of complex number. Yeah, so if time is complex, we have two time coordinates. Yeah. So this is one point, and the ideology behind all the theory is following. It is important, and this comes from, so it was the idea of Poincaré. When you have a particular solution, yes, so you are lucky, because you can write the variational equation. Here you look what happens near this particular solution. Yeah. Level. Simply here you have your solution phi of t, yeah, and you just make this variation I denote by y. Yeah, so this is the trajectory. So in the first approximation, when you act from right hand side into Taylor series, what you obtain? You obtain linear system of differential equations. Yeah. You can think that, okay, I just linearize my system. Yeah. So maybe it is easier to do something, and it is in fact yes. Yeah. First of all, there is a maybe one more remark. It is like when we have a function in one real variable, and we want to study how this function behaves. Yes, when we change independent variable, what we are doing, we expand in a given Taylor series. We take the first term, it is a line. Yeah, okay, this line catch a property of this function. If it grows or decrease, yeah. So we have something. So the linearization catch some property of all function. Here the same. Yes, nonlinear system left fingerprints in properties of this linear equation. So this is the ideology. Yeah, and the first implication is this is not trivial. Yes, when the system possess some number of first integral, the variational equation also possesses the first integral. Yeah, but you know, because linear part is not unique for a function, of course. So this is the same with first integrals. Yeah, so where here you can think, okay, I expand my first integral into the Taylor series, and I take leading part, and this gives me first integrals of linearized system. And it is in fact true. But the problem is that we want to have functionally independent first integral. Linearization can destroy functional independence. Yeah. So okay, we need something more. And this was already done. It is so-called Ziegler lemma. I call it fingerprints one. Yeah. And now we pass to the Hamiltonian system. And here you see there is hard part of my talk, because first time it appears I use differential Galois group. Yes, so, and we are blocked, so some remarks are necessary, yeah, for explanation. But first let me formulate. We have a Hamiltonian system, yes, so we have differential Hamilton's equation of motion. We assume we have a particular solution. Okay, we have linearized system, and what we investigate this linear system, and now there is a problem, because appears differential Galois group. So I have to switch to blackboard if somebody help me. So imagine that we have the system of linear differential equation of that form. Maybe I will write. Okay. Yes. H is a vector in Cn, yeah? And now I want to study this system, yeah? So I do the following. The right-hand sides can have, so assume that the right-hand side are rational, yes, so just to specify A of that is a matrix n by n, and in the field of rational function. Okay? So assume that, for example, if I have ij, so that there are rational functions, so assume that we have a singularity. So assume that there is a constant z minus, well, maybe I give an example, it will be quicker. So the coefficient, because rational, then they have usually singularities, yes, when the denominators of this function vanish, yeah. Yeah, so how to find the solution? Yeah. So for example, if I have just one equation, so let us say two equation, and my matrix is like that. Z here alpha z minus 1 beta z minus root 1 and here 2. Yeah? So we have, so this is our matrix of that. So we see we have singularity at 0, minus 1 and plus 1. Yeah? So if I write complex plane of a complex time, yeah, so xy, and so, and I have here, you know, I have 0, and I have 1, and here I have minus 1. Yeah? So now I can integrate my differential equation along arbitrary path here. Yeah? Go like that, maybe about arbitrary loop. Yes. Yeah? So fact that I started from this point and return to this point does not mean that I obtain the same. We have effect of monodrome. Yeah. So the function change its value when we continue, when we make continuation around the loops. Yes. So, for example, square root of complex number have this property. Yeah. If we have differential equation, yeah, we can just write system for fundamental matrix. So instead of vector, we just write matrices. Yeah, and we have matrix. When we make a continuation, we obtain another fundamental matrix, not initial one. Yeah. So, but what happened? Yeah. So these changes are described by constant matrix, because when we know from the theory of linear equation that the space of solution of linear equation is just isomorphic to Cn. Yeah. Yeah. So we have another combination. Yeah. So so I have part gamma. Yeah. Of that. I have fundamental matrix of that, and I make this continuation. I obtain new fundamental matrix, but this fundamental matrix, because of general theory, is just original fundamental matrix multiplied by a matrix. I will denote it M gamma from the right hand side, because I have to take the linear combination of columns. Yeah, and this is called monodromy matrix. In fact, this matrix does not depend on the particular choice of gamma, but on the homotopy class of this curve. So in this way, we have an anti-representation, as a matter of fact, of the first homotopy group of my plane with certain points removed, yeah, into the matrix group, yeah, into GLN, yeah, over C. So this is the monodromy group. And what Sigwintzew in his proof non-integrability of three-body problem used was this kind of group, yeah, because well, okay, so one moment, please. And now, when we study nonlinear equation, we have a solution. Assume that this is variational equation. Along this solution, we have this monodromy group. Now it is easy to prove the following. Original equation have a first integral. This equation has a first integral, but this first integral is invariant of this monodromy group. Very nice, yeah. But the theory of group invariance is well known and powerful thing. So we can formulate necessary condition for integrability using the monodromy group of differential equation. Yeah, done. And what? And it was done in the context of Hamiltonian system by Ziegler, and Sigwintzew in his proof of non-integrability of three-body problem used just this theory. From that point, it is just one big jump to the differential Galois theory. And now the question is, if you know, I asked that already, if you know something about usual Galois theory. So usual Galois theory says, oh, okay, we have a polynomial equation, and we want to know if we can solve more or less in the same way like we solve equation of quadratic equation, cubic equation, or quartic equation, just using radicals. The answer to this question was done by Galois, and this says the following. When I have equation and the coefficients belong to a certain field of numbers, yeah, solving differential equation, I ask where my solution live, yeah. So I have to find a bigger field which contains solution of this equation, yeah. Okay, and then the answer given by Galois is following. Okay, I presume that I know what is this field, the starting and the final. Then I have to investigate the group of field automorphisms which preserve the original field, yeah? And this group is just a permutation group, subgroup of permutation group. And Galois answer is following. If this group is solvable, then my equation is solvable by radicals. This is the very short course of Galois theory. Yeah? And now, what about this differential Galois? So in differential Galois theory, we talk about the differential equation. Yeah? We have a certain field, okay? Differential field. Yes, so I denote it. So here maybe, well, okay. So just for simplicity, K is just field of rational function, just example, and this D is just D over Z. So this is the differential field, yeah? And I have an ordered differential equation, yeah? So let us say Y and will be maybe Z. Linear difference equation A1 of Z n minus 1 plus blah 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 plus A0 of Z y is equal 0. Yeah, so this is my differential equation. And well, now from the usual theory, we know that, well, we have a space of solution and so on and so on. But when we pass to algebra, we are blocked by the request of purity. Yeah? So we have to define a differential field, which is the extension of this field, which contains all solutions of this equation. Yeah? So to prove this, it was a challenge. Yeah? Kolchin in 50s, 60s wrote a big book about this in general algebraic setting. Yeah, but anyway, for us it is not a problem because it is done. Yeah, it is like with Galois theory. We have to understand only what we are doing. Yeah, and then having this, we can define the differential Galois group. Yeah, so what is it? It is the group of transformation from one field to another. It must be an automorphism, differential automorphism. So derivative in the starting field is the derivative of the end field, such that it does not change the field when the coefficient belongs. That's all. And such a extension which contains all the solution of this equation is called Picapissio extension, blah blah. It is the beginning of 20th century. Yeah. That's all. And now we have to materialize this differential Galois group. What is it? Yeah? And it is easy to show that this is a matrix group. Yeah? So this differential Galois group is a subgroup. So in that case, it is a sub. So I write this group like that. It is a subgroup of G12. And well, okay, but there is one very important thing. This group is not just a group, it's an algebraic group. This is important because algebraic groups has a lot of good properties. Among other things, they have their own real algebra. Yeah. So and so what next? Now you see. Now we go in a parallel way, like with monotonic group. Yeah. And it was done by Morales and Ramis. Yeah. So why you talk about the monodromy group? It is already known that the monodromy group is a subgroup of this differential Galois group. Let us pass immediately to this differential Galois group. What we can prove? We can prove more or less what was done by Ziglin, but using the language of differential Galois group. And this Morales-Ramis theorem has a very beautiful theorem. Look, we have a Hamiltonian system. So we have the commuting group, if I can use this word of first integral, yeah, commuting set of first integral, and what we obtain? We obtain differential Galois group of variational equation, yeah. The identity component of this group must be also abelian. It means that the algebra of this differential Galois group is abelian. And this is, again, short introduction of application of differential Galois theory to integrability. Yeah? But in our proof, in an n-body problem, we cannot use this theorem because we talk about different kind of integrability. Yeah. So I skip because because I am late. So because of this problem and because what I said about the different kinds of integrability, we introduced the notion integrability of the fixed level of non-first integrals. Shortly speaking, it is like that we restrict our system to the level of non-first integrals. So this is the set S. So actually, I do not see. Okay, so we have a certain number of first integral. We take the common level, yeah, and then, okay, we say that this system is integrable when generally we have n first integrals as a number of degree of freedom of original system, yeah, but they has to independent, but only on this set. They have to commute, yeah, but only on this set, not in general, only on this set, yeah. Okay, so maybe like that. And so this is just the definition, yeah. And what next? This proposition is crucial because it allows us to apply differential Galois approach. Yes, so having this, we prove the following. So having this definition, we can show that okay, if the system is integrable in this restriction, then we can find differential fields generated by first integral such that the first of them are commute, but the other just such that their commutator are spanned by the first m vector fields generated by first integrals. Yeah, having this and using the result of Kariniena, Falsetto, Grabowski, Reniada, it is known that when we have this, the system is integrable by quadratures. And this fact allows us to apply differential Galois approach to the integrability. And again, we were happy because we have very important paper of Guy Casal, pupil of Malgrange, and using his result, yeah, you can say, okay, assuming that we talk about integrability, restricted integrability, then the necessary condition of integrability is the differential Galois group alone. So for a particular solution, yeah, given particular solution, it's not abelian. Identity components not abelian, but solvable. Yeah? So it is a change, and this is the difference between Morales-Ramis theory and this case. Yeah. Well, so now you see, we have to return maybe to the beginning. There is one detail which is important, and I point you. You see, the problem that in order to apply this old general theory of Morales-Ramis of differential Galois, we have to deal with differential equation for which right-hand sides are analytic function of complex variable or meromorphic function of complex variable. But because of this square root which appear here, our function, of course, is not meromorphic. Yeah? On the complex plane. Yeah? So what to do? So it is possible to avoid this, technically speaking, just introducing additional variable, and we can put everything to the framework where we can apply. Yeah. So return to the as I said, here we have this this term. Yeah. And Thierry Combo and I, together with Marian Przybylska, just describe what to do in such a case, what we can do. Yeah. So knowing this, okay, let's go. Okay. No. Yeah. Okay, so technically it is just we have to introduce additional variables, yeah, and then work with this additional variable. So our problem can be formulate the following: that we have a system defined on this set, common level of energy and angular momentum first integral, yeah, and we want to talk about integrability of here n-body problem on these levels, yeah, and our theorem can be stated very simply. For every choice of masses, for every choice of number, if it is only greater than 2, and for every choice of energy and angular momentum, except the case where both of these integral vanish, the system n-body problem is non-integrable on that level. Yeah. So, well, and now we pass to the, you know, I just want to in the last part I want to show you how collecting nice things from the past, it is possible to prove this theorem. So, and of course, it is necessary to supplement somehow this. Yeah. So there's first two explanation of difficulty of this problem. Yeah. So we have n plus 2 free parameters. Yeah. We have to cover all the cases. Yeah. First. For every of this choice, we have to find a particular solution of an n-body problem. If you know something about n-body problem, when n is greater than 2, you know that this is really, really rare when we know a particular solution. Yeah, the second problem, and then and this is the hardest part. Yeah, even if you have this solution, yeah, you write the variational equation for this solution. You have to investigate the differential Galois group or properties of differential Galois. Yeah, this system is 2n by 2n, or we can remove a certain number of equations because of restriction. Yeah, equation and differential Galois group. The theory is very powerful, but still till now, go to study differential Galois group for system of more than 2 equations is a challenge. Yeah? So all 3 parts are difficult. Yeah, and now, so about the particular solution. So for a long time, it is known what is called the central configuration in a body problem. Okay, you just think in the following way. I have a masses, I have to put them somewhere in the plane in such a way that relation between the forces acting on these points satisfies this relation. It means that the resultant force for each body is direct to the center of mass of the body, and it is like a like a harmonic oscillator force here. And to find this kind of configuration can be reduced to such a system of nonlinear equation. Yes, so I just write the formula in that way. And this problem was known for a long time, and Stephen Smale called this problem the problem for actually this century, 21st century. Yeah? But what is the problem? To prove that for arbitrary masses we have only finite number of central configuration. Yeah? So it was not connected with integrability. But why this central configuration was important for us? Because of the following. When I have a central configuration, I can quickly find a solution of n-body problem. Because I put this expression for position of all particles, and it appears that this factor and this function mu just a solution of a Kepler problem. Yeah, we know how the solution of this equation looks like. So I have a solution of n-body problem. Nice. Yeah, and having this, okay, I perform linearization. Yeah, so forgive me that I skip this formula. This is just algebra and analysis. Yeah? We have to calculate the Hessian matrix of the right hand side, put inside this particular solution, and explore the fact that gravity forces are homogeneous. So everything, when you put inside everything, what you obtain, our differential equation can be written in that form. So all matrices here, so this is vector has dimension n, so we have n second order differential equation. This matrix G is n by n, but the wonderful thing happened that this matrix is constant. It just depends only on the central configuration. That's all. Yeah, wonderful. Yeah. And coefficient are something like that, yeah. And what is known. So of course Euler was first who have found first central configuration when all bodies are along one line. Yes. Then the particular solution we talk about are just Kepler. I wrote here that they are elliptic Kepler problem. All the bodies are always aligned along a line. Here you have a center of mass, and they move each of them on ellipses with the same eccentricity, only with different same major axes. Yeah, but French scientist Lagrange found something more striking for arbitrary masses. We have found that there is another possibility that three bodies form equilateral triangle, and each of them evolve around the common center of mass along the ellipse. Yeah. So I will show you animation, but I have to switch. Where we have this. So you see, this is Euler solution. I hope you see it. Yeah. And this is true integration of differential equation. I do not cheating with this. This is have to solve differential equation. And if you try, you will notice how unstable this solution is here. So we have Lagrange. So this is a Lagrange solution, which is very educative to try to find initial condition for both these cases and to show. And I will show you, in order to do not break the rest of my talk, another solution. Moulton had found, I will talk about this. We have 5, so this is again central configuration like Euler, yeah, but we have 5 bodies, yeah. Nice, yeah. So that's all. So demo is over. Yeah. So this is the Moulton solution. So yeah. So I skip this. Well, no. Skip this. And okay. And you see, well, okay. So we have a central configuration, but the problem is following. Only in Lagrange solution, we have explicit form of coordinates of the points for this solution. In the case of Euler, they are given as a solution of 5th order polynomial equation. So we cannot solve this by the Galois theory. Yeah? So with Moulton, it is even worse. We know that it exists, but we do not have slightest idea how it looks like, except when we find them numerically. So it seems that to apply our approach, we are restricted only to the Lagrange, and this is very misleading. So we noticed earlier that in some sense, Euler solution is better than Lagrange, and the fact that we don't know precise position of this, it is not so important. Important is what is important. You will see. We assume that okay, we know we have Moulton solution, collinear points. So you put them one by one along the line. So we write, variational equation, and we notice that this matrix which governs the variational equation has a very special structure. And well, okay, using algebra, fact that we can diagonalize it, a moment I will explain, we reduce our equation to the product of differential equation. Yeah? Yeah? For each body, we have one equation of that form. Yeah? And as I said, it is necessary to find something important. So it was Conley who proved the following theorem. When you have this matrix C, yeah, so he proved that it has real eigenvalues, yeah, it is diagonalizable, and 2 of eigenvalues, one is 0, one is 1, and the remaining one, that this is the most important for us, are greater than 1. And what we need only those eigenvalues which are greater than 1. Yeah? So And why? Because we prove that exactly those those differential equations corresponding to those eigenvalues correspond to variational equation or our restricted system to this manifold when we deal in which we deal with. Yeah? Yeah. Nice. So now, so this is Conley. So in effect, we have to investigate such a system of differential equation. Yeah, and this matrix G is very special. Yeah, so we have particular solution. Yeah, and what we can prove. So look, we have this system. So still we have 4x4 system. Yeah. And to simplify our life, yeah, what we can do? We can transform this system to a product of two subsystems, 2x2. So we split, we make next step of splitting, yeah, and you know how we find this solution. Again, this is it is possible to find that this kind of problem was investigated by a German, I don't know, Schanner probably, for the restricted three-body problem. And we just generalize his result and obtain that in fact we can split this system to two systems of 2x2 differential equation. And having this, so it was our destination, because we know what to do with this system. We can investigate the differential Galois group. Yeah. Okay, this is technical, but anyway, it was the let us say the final accord of our work to investigate this system. Yeah, and so if we assume that eccentricity is different from zero, this delta is different, parameter delta connected with lambda is different from zero, but in our case it is. Yeah, so we prove what? That the differential Galois group is not solvable. So it is. This is what we need. In other words, what does it mean? It means that we prove our theorem in the case when this HC square is different from minus me. Yeah? So if C is 0 and H is equal to 0, our proof is already done by Thierry alone, and it remains only just one case when the orbits corresponding to central configuration are circular. Yeah, so it seems that it is the easy case. No, the variational equation for circular orbit are solvable. Differential Galois group is not that solvable. It is just abelian. So it gives nothing. It was necessary to find some different particular solution. And you know, I think that nobody knows that in the Kepler problem, except real circular solution, there are complex solutions. And this complex solution for Kepler problem is given by this formula. F of u is equal to 1 plus e to the power nu. Yeah. So it gives this function. It gives a solution of Kepler problem. And using this solution, we repeat. We prove that the splitting of the variational equation 4x4 still is possible. And applying no algorithm, we have done. Yeah. So, and this complete our proof. Yeah. So I thank you very much for your attention. I talk longer than I expect. But anyway, I am willing to answer to any of your questions, critical remarks to listen.
So I have a question. You have this matrix P.
Yeah.
And you said that some of these eigenvalues need to be bigger than 1.
Yeah.
So is it something related to Latin of exponents?
In some sense, yes. Yeah. So this lemma of Conway proving this is a masterpiece. You know, it is not easy because the problem is that we don't know this matrix. We know that this central configuration exists, but it's coordinated. So the element of this matrix depends on coordinates of this a priori unknown but existing central configuration. Yes. So it was a challenge to prove this, and Conley was able to. Yeah.
Other questions?
So it seems that nobody understands.
Maybe from the zone. Well, so if there's no question,
Thank you.
your question.
Sure.
Yeah, I'd be happy to ask, but I think Maciek had a question before me, so I don't want to squeeze myself in front. Maciek.
Andrzej, I'll be brief. So that it was very nice. I was going to ask this: in the presence of positive cosmological constant at the non-relativistic level, you could model it by taking your potential and adding a repulsive harmonic term. So the force increases with the distance. Now, if you do that, then you can have static configurations which are really static. So the gravitational force and the cosmological forces balance. So question is, at the level of your formalism, if you need solutions to variational equations, can you make it better by adding this cosmological constant? And then you can put points, let's say, on the sphere, and nothing moves, and you have an explicit static solution to do your Galois theory with. Thank you.
So you mean that if I add to Newton equation just the harmonic term?
Yes,
here?
but it has to be a harmonic term with reverse direction. So you want, not minus omega square sort of r, but plus omega square r. So it's like a reverse harmonic oscillator.
So do you see my slide?
I see your slide.
Yeah. So I mean, you said, okay, add here, yes, something plus omega squared, sum of this difference.
You just are.
Well, that's right. So you would probably need to, if you pick an origin, you could say that you're adding plus omega squared times plus the connecting vector from this origin. Right? So you want to add a repulsive term.
From the center of mass, yes. So because this equation, so because this is written, well, it's not visible, but it's written in the center of mass. You have to assume that the center of mass is equal to 0. Yeah. So you have to just add here omega squared Ri. Yes.
That's right. I would be tempted to add all the sum of all the r's divided by n, but maybe it's a technicality. But you add something which makes it repulsive for all I.
So if I have those equations, so we have to exchange email, and you write me the formula, then I can start to think. Yeah. but you know, the problem with arbitrary n is that, okay, we restrict to the n sum, 2, 3, or 4, okay, we can talk about, but for generally the difficulty is that we need particular solution for every n. Yeah. So if we change, for example, masses to charges, then the problem is that we have to prove that there exists at least one central configuration if we just have a plan to apply, you know, approach I presented. Yeah. In the case of charges, it is not so obvious that they are, and in fact, it was difficult. It was difficulty which prevented us to extend our result to uncharged problem. Yeah.
Sure, thank you.
So maybe I can ask.
So if you please send me, you know, a question you have in mind, then we can exchange.
So maybe I can ask my question now. I loved your historical part with all the details. I didn't know most of them, but so what I eventually got lost in how much your result improves on previous ones. Could you just say it in a nutshell?
Yeah. So Thierry Combo proved that the n-body problem is non-integrable in the Liouville sense. Yes. So it belongs to him. Yeah. In the Liouville sense. Here we prove much more stronger result because we restrict n-body problem to the arbitrary energy and angular momentum levels. Yeah. So we have you know, infinite number of dynamical system, numbered by the values of energy and angular momentum integrals, yeah, values. Yeah. So this is why this result is much stronger. As I said, there are examples of systems which are non-integrable in the Liouville sense. Just for if you find even
no
energy, okay.
What subset of the phase space you take, which is invariant under the flow, it will not going to be integrable. That's the.
Can you repeat your question?
Take any subset of the phase space which is invariant under the flow. It's not going to be on this. The system will on this subset will not be integrable either. That's the bottom line.
So simply, if I so if you okay, imagine that you have the Hamiltonian system. You have only energy. Yeah, fact that the system is integrable on a specific value of energy does not mean that it is integrable just for a near energy level.
Right.
Yeah. Yeah. So simply integrable cases are separated. Yeah. Yeah. So yeah.
Okay, and so I know that this notion of not integrable is, well, it's telling you that this behaves in a funny way, but it doesn't really tell you how things behave. So does your theorem give some more information about it, or it just telling us, well, it's not behaving nicely?
So you know, so this differential Galois theory tell you something about if you say how to say it tells you about the properties of solution as a function of complex time. Yeah. So I give you just a very simple example. If you take a function 1 over 1 plus z squared, if you look at this as a z is just a real number, you can prove that the Taylor-Searle expansion at z equal 0 has a radius of convergence equal 1. And you don't understand why it is like that, because at one, nothing special happened, yeah? But when you pass to the complex, you immediately understand, okay, in plus minus I, you have
A singularity.
a singularity.
Mhm.
Yeah, you have a pulse, yeah?
Mhm.
And nothing to prove, yeah? In the first case, you have applied test of convergence, radius of convergence, blah, blah. Everything works perfectly, but you have to make a lot of effort to prove this, although from the point of view of complex analysis, very simple. And well, to answer directly to your question, this differential Galois non-integrability does not say anything about the dynamical reasons of non-integrability. There are some reasons, for example, of non-integrability, splitting of separatrices and so on, but this theory does not describe dynamical properties of the system except this integrability. That's obvious. So
Okay,
this is the.
Thank you. Yeah, it's
Okay.
still a very interesting, right? But I was just wondering if there is something more than one can get out of this.
So in some cases, you can connect this result of Galois non-integrability with the dynamical effect. For example, in the case of splitting of separatrices, there are some results. We say, okay, if we are splitting of separatrices, then the differential Galois group is such and such, blah, blah. Yeah, something like that exists, yeah?
Thank you very much.
You're welcome.
I have a question. So there was a special case of energy zero and angular momentum.
Yeah.
So, and your proof is not covering.
So we cover all the cases except when both of them are zero.
And do you expect it's also non-integrable? And
You know, I answer you as a referee. Yeah, everybody expected this is non-integrable, but this is not an answer. Yeah, yeah. So yes, we can expect non-integrability, but the reason is the following: that for this value of first integral, we have let us say. I abuse words here, massive probability of collisions here. Zero angular momentum is a necessary condition of collision, blah, blah, something like that. Yeah? We have collision with the three body problems. And in that body even more. Yeah.
okay, thank you. So another questions? So now it's
Thank you very much.